Hey guys, can I please have a lick of your ice cream?
Sure, but only one lick.
And one from one of us, not both of us. You need to work on your diet.
You're right. I should do some measuring so that way I can get the most out of my lick.
Yeah, well, my cone top is elliptical.
And mine is circular.
Let me think.
Conics get their name because they are derived from slicing a cone or two cones stacked perfectly on top of one another, called a double-napped cone, like this. When slicing double-napped cones with a plane perpendicular to the bottom of the cone, you create a hyperbola. By slicing the cone parallel to the side of the cone, a parabola is created. By slicing the cone at a slight angle, you make an ellipse, also the shape of one of the ice cream cones in our problem. By slicing the cone straight through, parallel to the bottom of the cone, we create a circle. This is the shape of Martha's ice cream cone. Let's start by finding an equation for the elliptical ice cream surface. The standard form of an ellipse is x squared over a squared plus y squared over b squared equals 1. In the equation, a equals the semi-major axis and b equals the semi-minor axis. We can find these in the ice cream cone by finding half of the semi-major and semi-minor axes. So in the equation, a squared is 3.24 centimeters squared and b is equivalent to 2.56 centimeters squared, making the equation for the elliptical ice cream cone x squared over 3.24 plus y squared over 2.56 equals 1. In order to graph an ellipse, one has to first know the two foci. This is because, according to the definition of an ellipse, it is the set of any points on a plane such that the sum of the distances from any point on the curve to the two foci is a constant. So this means that if the two foci are at a set position and you have a constant distance from the points to a point on the curve, the ellipse, every point is going to be, the sums are going to be equal. So in order to find the foci, one has to first know that A, or the semi-major axis, is equal to the hypotenuse of a triangle that with the legs of the semi-minor axis and the point from the center to the foci. So to prove this, one has to see that when you go to the point which is lined up with the foci, so it has the same y value as the foci, then the distances are from this foci to the end, and then there's another distance from the second foci to this intercept. And if you were to take this smaller distance right here and put it right here, then you would create the full major axis. So then if you go to the point which is perpendicular to the center of the ellipse, you see that these two distances must be equivalent. So then if the whole string equals the major axis, then half of it has to equal the semi-major axis, which is equivalent to A. So if we use the Pythagorean theorem, a squared plus b squared equals c squared, which in this case would be b squared plus c squared equals a squared, we can change that to c squared equals a squared minus b squared, because c squared gives us the foci. In the ice cream problem, we know that a squared is equivalent to 3.24 and b squared equals 2.56. We found this by finding the semi-major and minor axes. So this comes down to C equals about 0.82, meaning that the foci of the ellipse are negative 0.82, 0, and 0.82, 0.
See here, this is the ellipse. The foci are located at 0.82, 0, and negative 0.82, 0. We found these by using b squared minus a squared equals c squared because we knew the semi-major axis and the semi-minor axis.
To graph our circle of our cone, we use the equation x minus a squared plus y minus k squared equals r squared when the center of the circle is at hk and the radius is r. The equation for our circle with the origin at the center is x squared plus y squared equals r squared. That is the same as the equation above, except we took out the h and the k because they're 0. The center of our circle was at the origin, and we knew that the radius was 1.6 centimeters. So on the computer, we put our circle, the center at the origin, and the radius of 1.6 centimeters.
This is the graph of the circular cone, and the radius is 1.6 centimeters, just the same as the elliptical cone's semi-minor axes.
Now that we have graphed the two circular and elliptical cones, let's find their surface area. The area of a circle is pi times radius squared. In this case, the radius of the circular ice cream surface was 1.6. So the formula would be area equals pi times 1.6 squared. This comes down to area equals 2.56 pi centimeters squared. Now let's find the area of the elliptical ice cream cone. The formula for an ellipse is area equals pi times AB, where A is the semi-major axis and B is the semi-minor axis. In this case, the semi-major axis is 1.8 and the semi-minor axis is 1.6. So the area is pi times 1.8 times 1.6. This comes down to the area of the ellipse equals 2.88 pi centimeters squared. So, as you can see, the elliptical ice cream cone has a greater surface area.
I'm going to choose Chase's ice cream cone because it has a larger surface area.